All right, the roll sheet is floating about, so if you are attending class via Zoom, please type something into the chat so that I'll know you are here while I attempt. Oh, that's the reason it's not showing up on the screen. I forgot to plug that in. To do it. All right, so looks like 8 people have said that they are here. That's great. I don't know. Close that, share my screen. Okay, so today is in some shape or form actually going to be a little bit of a review of some of the first topics that we covered way back in Circuits 2, but they will be slightly enhanced. And then we're gonna move on to bigger and better things very shortly. So we're gonna be talking about operational amplifiers. That is not my stylus. And the book details a little bit of basic background information about an op amp. So to not totally bore you guys to tears, I'm just going to skim over that kind of good stuff. So here's our circuit schematic symbol for an op amp. We have a power supply terminal VCC plus, a power supply terminal VCC minus, an output pin V out, a non-inverting input pin, which our textbook chooses to use the notation VN1 for the non-inverting input pin. And then we have our inverting input pin, VN2. We are aware, I hope, or you were in a coma during the entirety of Circuits 2, that there is a practical op-amp model that looks something like this. Let's call this guy RN. Here's VN1, VN2. Here's ground. R out. V out. And this guy right here is AVOL times VN1 minus VN2 based on the terminology that the book uses, where all of those voltages, VN1, VN2, and V out, are assumed to be with respect to ground. For an ideal op amp, which is other than those few things I forced you to do way back in Circuits 2, you've only been dealing with ideal op amps. For an ideal op amp, Rn is equal to infinity, AVOL is equal to infinity, and R out was equal to 0 ohms. And one thing that the book points out that we did not cover in Circuits 2 is that an ideal op amp also has an infinite speed. So what that means is that an ideal op amp can instantaneously respond to any input signal you give it, whereas a real op amp has things like capacitors and such inside that cause some RC delay, which we'll explore in much more detail later. So from our basic figure here, when we have an open circuited load or output terminal, our characteristic equation for this guy is going to be V out is equal to AVOL, our open loop gain, times the difference between VN1 and VN2. So an operational amplifier, and this is again a complete rehash of what we learned in circuits 2, doesn't amplify a particular voltage signal. It amplifies the difference between those two voltage signals. So if we were to apply a signal to VN1 while holding VN2 at ground, so if we had something like this, our response curve should look something like this. If this is VN and this is V out, we should get a straight line where the slope is simply the open loop voltage gain. Now we know that that's not technically true in all cases, right? This is only true if we're operating within the linear range of the amplifier, because we know that saturation distortion exists. And so for what's effectively a comparator like this, we should really expect to see that once our voltage increase, our input voltage increases past a certain threshold, we should see that the output saturates to VCC plus. And if our voltage, our input voltage is sufficiently negative, our output voltage should saturate to VCC minus. The textbook does a very, very poor job of acknowledging saturation distortion, except for one circuit in there. So I'm just trying to remind you that that does exist. It plays a huge role in the design. Your output can never exceed your power supplies. All that kind of good stuff is still absolutely fair game. In the event that we hold VN1 at ground, let's do it down here. Oh wait, ground. And apply our input voltage here at the inverting terminal. We get the following response. Let's see. Crap, that's not what I wanted to do. So something like this, where this is VN, V out, and we have a slope of negative AVOL. So the input exactly follows the output, except it's multiplied by a factor of 1. And again, we are assuming this graph is only for the linear range of operation of the amplifier. So what we're going to be spending most of our time today doing is looking at areas where the open loop gain of our system is non-infinite. So it has some finite value, and we're going to see how that affects our response, so our input-output characteristics of our amplifier, focusing particularly on the gain. There's one important caveat here that the book uses, which we're going to hit over and over and over again, and that is that if we rearrange our characteristic equation, we find that V out divided by AVOL is equal to VN1 minus VN2, which implies that VN1 must be approximately equal to VN2. And again, the textbook says this as kind of a fact. We know technically this is only true for negative feedback systems when the operational amplifier is working in the linear range of operation. So another little caveat here. All right, so Now let's jump into some op-amp circuits. Let's first look at what's called a buffer or unity gain amplifier. And so that circuit is going to look something like this. By the way, if I am going too fast and you guys want to ask a question, by all means do so. But since this is largely review, I'm going to assume there's not too many. I'm not trying to shame you into not asking questions or anything by any stretch of the imagination. I'm going quickly because I believe that most of you know all of this stuff. All right, so this is a unity gain buffer. So if we have an infinite open loop gain, what can we say about this guy? Anybody have any ideas? What's the relationship between V in and V out going to be? Any thoughts? Under the constraint that our open loop gain is infinite, meaning the voltage that is present at our non-inverting input terminal has to be exactly equal to the voltage that is present at our inverting input terminal. Does that help anything? So, what is the voltage present at the non-inverting input terminal? Vin, all right? And what is the voltage present at the inverting input terminal? Vout. And so if the voltage at the inverting input terminal and the voltage at the non-inverting input terminal have to be equal to each other, then how does this thing work? Vin is exactly equal to Vout. Okay. And so I'm going to call this AVCL, the closed loop voltage gain will be the ratio of the output voltage divided by the input voltage, and it has a value of 1. That is why this is called a unity gain buffer, because it has a gain of unity or 1. All right. So fairly trivial circuit to analyze if we have a finite open loop gain AVOL not equal to infinity, I can say that Vout is equal to AVOL multiplied by the voltage present at the non-inverting input terminal, which is Vin, minus the voltage present at the inverting input terminal, which is Vout. So this is my equation, just using my characteristic equation there. And I can algebraically rearrange this guy, and I find that my closed loop voltage gain is simply AVOL divided by 1 plus AVOL. And so I have a non-unity gain buffer here, right? As AVOL approaches infinity, the gain of this guy approaches 1. But if we have a poorly designed amplifier wherein the gain was, let's say, 20 volts per volt, or let's say 19, because that'll make the math easier to do in my head. So if the if AVOL were 19, then we would have 19 over 20 is 0.95. So instead of being a 100% input, output follows the input, only 95% of the input gets passed to the output. So for a practical op-amp circuit, we are expecting to see that our closed loop gain is going to be a little bit less than what we would expect from an ideal case. And we're going to explore that significantly more in depth here when we talk about non-inverting and inverting amplifiers. AVCL. So CL stands for closed loop. AVOL is the inherent gain of the amplifier, and that is the open loop gain. Obviously, this is a closed loop gain because we have a closed loop feedback path between the output terminal and the inverting input terminal. Yes, sir. So that's OL for both there. Yeah. So the closed loop gain is AVOL divided by 1 plus AVOL. Sorry, yeah. Ooh, stop. I'm trying to decide here on the fly if I want to adopt a different notation for closed loop gain and open loop gain so that it's going to be less confusing. Well, I think the issue here is that the O and the C look too similar. So if we still have an O and a C, then we run into an issue. So let's change this. Let's say that AO, all right, so from here on out, AO open loop and AV closed loop. So that's easily differentiated, like you can tell the difference between them. Okay. So I'm going to pre-apologize because my notes are all using AVOL and AVCL. So if I make a mistake, yell at me and I will fix it. Okay, so I feel like this will knock out some ambiguity. All righty. Okay, so let's look at a non-inverting amplifier next. So our circuit there stupid pen thing is so sensitive. It is going to look something like this. And the textbook chooses, sorry, the input voltage here, Vn. The textbook chooses to put the resistor R1 in the feedback position and the resistor R2 between the inverting input and ground, but that goes against everything I've ever taught. And since I've had some of you since literally the freshman engineering class, I'm going to use the convention that I have adopted throughout every circuits class I've ever taught any of you, and put R2 in the feedback position and R1 between the input and ground. So what that means is if you look at the textbook, you're going to see everywhere I have R1, you will see R2 and all that kind of stuff. I just want to make sure that if you're studying by the textbook, you don't go through and be like, oh, he screwed up everything. No, changing the position of the resistors. All right. So when we have a finite open, or excuse me, an infinite open loop gain, so if AV is infinitely large, excuse me, A naught is infinitely large, then our closed loop voltage gain for this circuit should be what? Anybody remember this, or do I have to derive things? No, because those resistors change stuff. All right, well, I'm not going to derive it. It is 1 plus R2 over R1. That should be familiar. If not, by all means, go back. All my Circuits 2 videos and all that crap are on YouTube. Learn this shit in your own time, because you should know it by now. Basic review stuff, okay? For a finite open loop gain, so A naught is not equal to infinity, then again, we're going to have V out is equal to our open loop gain A naught multiplied by the voltage present at the non-inverting input terminal, which is V in, minus the voltage present at the inverting input terminal. So I'm going to call this guy right here Vx, just an arbitrary nodal voltage with respect to ground. So Vn minus Vx, and I can say that Vx is simply V out times R2 over R1, excuse me. Vx should be race. R1 over R1 plus R2. So I made a mistake there on my notes originally. Right, so that's just using simple voltage division, right? So Vx, the voltage with respect to ground, is just going to be V out because that's the total voltage drop over R1 and R2, where we are making the assumption that no current can flow into the input terminals, or at least the current flowing in there is going to be very small. Substituting our relationship for Vx into V out gives us, put over here, a V, our closed loop voltage gain, is going to be A naught, our open loop voltage gain, times 1 plus A naught times R1 over R1 plus R2. So we can see that the looks significantly different here. And if, let me go to the next page. A naught times R1 over R1 plus R2 is much greater than 1, which seems pretty reasonable since A naught is usually somewhere on the order of hundreds to hundreds of thousands volts per volt. We can use a Taylor series expansion of 1 over 1 plus x is approximately equal to 1 minus x to get closed loop voltage gain AV will be approximately equal to 1 plus R2 over R1 times a factor of 1 minus 1 plus R2 over R1 times 1 over A naught. This quantity right here, 1 plus R2 over R1 multiplied by 1 over A naught, is what we're going to call our gain error, epsilon. Okay. So this is really what's telling us how much our practical gain differs from our ideal gain. Okay. And notice that we have our nominal gain over there on the left-hand side. So let me draw a squiggle under this. So this is our nominal or ideal gain. It's multiplied then by a factor of 1 and has a little bit subtracted away from it, okay? So the gain error is a measure of an amplifier's accuracy. So typically, circuits with very high nominal gains tend to experience larger gain errors. And so if we have a system where A naught is, let's say, 20,000. And we have a closed loop gain of 5 volts per volt. Then our gain error is only going to be 0.025%. If we bumped our closed loop gain to 50, we would see that our gain error increases by a factor of 10 to 0.25%. And finally, if we jumped it up to 500, we would expect to see our gain error increase by another factor of 10. And so it's up to 2.5%. So gain error is something that's going to have to be minimized in circuits. Now, a gain of 20,000 is low for a very well constructed or very well fabricated and very well designed operational amplifier. Typically speaking, we would expect our gain to be literally 10 times higher than that, if not more. The amplifiers that we've been dealing with based on our basic BJT circuits and all that kind of stuff, which are the building blocks of op amps, has been around what? 7 to 100, you know? I think probably somewhere close to 100 would be the absolute maximum that we've seen. So if we used one of those as kind of a fundamental building block without putting all the extra pieces that protect and increase the stability, we should expect to see gain errors in a closed loop system of around 50% or higher. So we're going to be spending a lot of time later on in this class talking about how we're going to mitigate those type of things and how we can construct it from the bare bones operational amplifier, which is really just a differential pair, which is 2 common source amplifiers with their tails tied together effectively, to how we can introduce other stages to increase the gain while doing other things. So all of this is building off the stuff that we did in the last quarter, although it may not technically seem like it yet. All right, so another question that you may ask is, why would we use op amps versus the transistor amplifiers that we spent 3 months or so figuring out how they work and all that kind of jazz. So for the transistor amplifiers, let's take a MOSFET amplifier, right? The voltage gain of the system was largely dependent on the transconductance of the amplifier circuit, right? Well, the transconductance in turn is dependent on a couple of parameters, UN, Cox, W over L, the aspect ratio, and then depending on what way we want to look at it, the voltage, the current, etc. So Cox is effectively fixed. It's a process parameter, can't really do anything about that whatsoever. The width and the lengths, we can do things to increase the gain. So if the W over L ratio is larger, we can make the gain go up. The W over L ratio is smaller, we can make the gain go down. Mu N Cox, or excuse me, Mu N or Mu P if we're dealing with a PMOS transistor is the thing that's going to give us the biggest pain in the butt, because that is based on electron mobility for NMOS transistors and hole mobility for PMOS transistors. So if the temperature changes, we should expect that that value changes significantly based on our knowledge of solid state physics from 334 and moving forward, okay? Then we have to deal with things like process variations, meaning that if you design your masks in electric and all that kind of stuff, it's assuming that everything is lined up exactly perfectly and all the sizes are the sizes. But if the technician who's feeding the mask into the machine slightly misaligns things, I'm talking a fraction of a degree, that will literally change all of your parameters of how your device behaves. For an operational amplifier, our gain is established by a ratio of resistors. Now, these resistors contain semiconductor material and all that kind of stuff too, especially if they're integrated on a chip. They're obviously some sort of either N-well, P-well, polysilicon, etc. So because they're created using semiconductor materials, they have some, the individual values of the resistance has some dependence on temperature and process variation as well. But the ratio does not, right? If the temperature increases, both resistor values will increase at the same rate. If there is a misalignment, both of the resistors will be just as misaligned, so that that ratio is effectively going to stay consistent. So this is why op amps are so integral to creating good amplifier circuits, is because by their inherent nature of everything is established by the resistances you put in that feedback loop, you can get very, very stable behavior over a wide range of temperatures, even in pretty crappy fabrication conditions. All right. So let us now move to inverting amplifiers. If I can get hold of my pen here. What time does this class end? 10:45? Okay. Okay, so an inverting amplifier is going to look something like this, or not something like it. It's going to look like this. Notice that I've put my non-inverting input terminal on the bottom now. Doesn't change in any way, shape, or form how the circuit behaves, just to make things look nicer. So this is our basic inverting amplifier. Again, it's inverting because the input is applied at the inverting pin. When A naught is equal to infinity, does anybody remember what the closed loop gain of this guy should be? negative R2 over R1. Thank you. When we have a finite open loop gain, we can say that, let's call this voltage here Vx again. So V out is going to be A naught times 0 minus Vx. So let's just say negative A naught Vx, which means Vx is negative V out over A naught. The current flowing into that node Vx has to be exactly equal to the current leaving that node Vx flowing through the feedback resistance. So we have Vn minus Vx divided by R1 is equal to Vx minus V out divided by R2. And with a little bit of algebra, we get our closed loop voltage gain, AV, is negative 1 over A naught plus R1 over R2 times 1 over A naught plus 1. And rearranging these terms ever so slightly gives us negative R1 over R2 plus 1 over A naught times 1 plus R1 over R2. All right. So in this case, I don't know why Microsoft Store opened up, other than my hand probably rested on something dumb. If A naught times 1 plus R1, R2, sorry, 1 over A naught times 1 plus R1 over R2 is much less than 1, using that same Taylor series expansion. Approximation. We get our closed loop gain, AV, to be approximately equal to negative R2 over R1 times 1 minus 1 plus R2 over R1 times 1 over A naught. So we have the exact same gain error quantity as before. And so this easily shows that when A naught goes to infinity, our closed loop gain approaches the ideal case, which is exactly what we should have seen in the last one as well. But when it's finite, we see that we wind up taking a little bit away from our ideal case. All right, so the textbook addresses inverting summing amplifiers as well, but it does not actually address it with a non-infinite gain, which would be literally the exact same analysis that we did in circuits 2. So I'm not going to bother doing that because I'm adding no extra information whatsoever. Problem, I think it's 8.31 in the textbook, asks you to go through and derive stuff for a non-infinite gain. It's not that hard. I actually did it, but I didn't bring the notes down here. But it doesn't really enhance anything. Where things start getting a little bit weird and wild is when we look at differentiating and integrating amplifiers. There we go. So let's start, if I can get this thing to behave how I want it to, with a differentiating amplifier. All right, so for a differentiating amplifier, we have some time domain input signal, Vn as a function of time, so Vn of t. That is applied to some capacitor C. Ground our non-inverting input, and our feedback loop contains a resistor R and we take our output at the output terminal of the op amp. So the textbook analyzes this circuit using in the Laplace domain, which I couldn't do way back in circuits 2 because you hadn't had Math 245 yet. It actually makes the analysis much, much easier. So when we have an infinite open loop gain, we can see that, let's see, how do I want to look at this? Sure. All right, so the current that's flowing through that capacitor has to be the same as the current flowing through the resistor. And we know that our voltage at node X right here for an infinitely large open loop gain must be 0, right? So that tells me that Vn divided by 1 over SC, my Laplace domain representation of the impedance of a capacitor, is equal to negative V out over R, which means that my voltage gain, AV, or my closed loop voltage gain, is just negative RC times S, my Laplace variable. You guys have had 321, right? So 320, ELEN 321 last quarter was linear systems, and yes. So just as a refresher, V out would then be negative RCS times Vn. So what does it mean when you have S multiplied by your input function? Pardon? Derivative, right. So from that, we can easily see then that V out as a function of time is negative RC times the derivative of our input signal as a function of time, without having to jump through the numerous hoops we did when we analyzed this entirely in the time domain way back in circuits 2. For a finite open loop gain, we have V out is equal to negative A naught times Vx, because this is nothing more than a inverting amplifier, except that that capacitor is taking the role of R1, right? So our input out, our relationship there should remain unchanged. We will have now, since Vx is going to be non-zero, because our open loop gain is not infinite, we will have Vn minus Vx divided by 1 over Sc is equal to Vx minus V out divided by R, which gives us a closed loop voltage gain of 1 plus 1 over A naught plus RCS over A naught in our denominator, and negative RCS in our numerator. So obviously, as A naught goes to infinity, our closed loop gain goes towards its ideal value. One thing to point out here, though, is that when we have a practical op amp, we now have a pole that we have to concern ourselves with, right? So there will be a place where our voltage gain will approach infinity. So our pole location here, or pole frequency, SP, which occurs when the denominator goes to zero. Yeah, when the denominator goes to 0, is at negative A naught plus 1 divided by R times C. So at very, very high frequencies, assuming or in the left-hand plane, but at high frequencies, we will see that our amplitude is going to blow up. So the non-infinite gain, or the finite gain here, does create a couple of issues. It introduces a pole, and obviously then we also see that since the denominator term here is where all of our A naughts show up, or our finite gains show up, this is lowering the overall gain of the system. And now let's talk about integrating amplifiers. All right, so an integrating amplifier is just a differentiating amplifier where the position of the capacitor and the resistor have switched. So still going to have some input voltage that varies with time. Here is our resistor value R. Ground our non-inverting terminal. We now have the capacitor in the feedback position. We take our output at the output terminal. When our open loop gain is infinitely large, let's call this guy Vx again. So when the open loop gain is infinitely large, Vx must be equal to 0, because the non-inverting input pin is at ground, so the inverting input pin must also be at ground since VN1 has to equal VN2. So our current, we're going to have some current that's flowing through that resistor R. That same current must then flow through the resistor C. And so we get VN over R has to be equal to negative V out divided by 1 over SC, which gives us a closed loop voltage gain of negative 1 over RCS. Notice that there is a pole here. So at DC, effectively, our amplitude is going to blow up. So our gain goes to infinity at omega is equal to 0. Time domain, just for those of you who are unfamiliar with it. So if multiplying by S was differentiating, dividing by S is integrating, right? So this is why it's an integrator, and we get V out as a function of time is negative 1 over RC times the integral of Vn dt. Again, much, much shorter than how we did it, doing everything in the time domain. When we have a non-infinite open loop gain, we can say that V out is equal to negative A naught Vx, which again implies Vx is equal to negative V out over A naught. Our current flowing through the resistor is Vn minus Vx over R. That has to be equal to the current flowing through the capacitor, which is Vx minus V out divided by 1 over SC. Doing a little algebra and rearranging, this gives us a closed loop gain of 1 over A naught plus 1 over A naught times RCS negative 1 in the numerator. So for an infinite open loop gain, we can see that our closed loop gain goes to infinity at omega is equal to, or S is equal to 0, right? So AV goes to infinity when S is equal to 0. What happens when S is equal to 0 for a finite gain? Oh, sorry, I guess technically this should be negative infinity. So we will see that AV is going to approach negative A naught when S is equal to 0, right? Because if S is equal to 0, this whole term goes away, and so we have negative 1 divided by 1 over A naught is just negative A naught. So it even lowers our infinitely large gain in the worst case scenario when we have a finite gain. We are going to have a pole again. but our pole is not going to occur at 0. It's going to shift to the left slightly. So our pole will occur at -1 over 1 plus A naught times RC. So I believe, for the most part, this sums up all of the amplifiers that you should be familiar with the exception of the inverting summing amplifier, which is really just a special case of an inverting amplifier with multiple inputs. So that's why it's not particularly difficult to analyze. You just throw an extra input in there, and I don't know, you can use superposition if you feel like, or whatever floats your boat. So the next section in the textbook goes over a few amplifiers that we have not yet seen. So I only prepared notes on one of them because I wasn't sure that we'd get this far. So we'll spend maybe 5 to 10 minutes on this and then get out of here. So this is so to this point, the operational amplifier that we have been dealing with has been capable of performing linear mathematical operations, right? So we can add signals, we can subtract signals, we can integrate signals, and we can differentiate signals. So our first nonlinear operation that we can do with an op amp is what's called a precision rectifier. And this is where we start incorporating the stuff that we learned in 335 into op amp circuits. So a precision rectifier looks like this. We have an input signal that is going to be applied directly to the non-inverting input terminal. We are still going to have negative feedback, but between the output terminal of the op amp and the inverting input terminal of the op amp, we are going to place a diode. And we are going to take the output at the inverting input terminal. So our output of our system here is not the output pin of the op amp. I know it's a little hinky, but that's how it's built. So we're going to call this voltage Vx, and we also need to create a path to ground. So I'm going to put a resistor here, R, and this is my diode D. How this guy works is actually really, really interesting. So let's consider things first, ideal diode model, to get conceptually what's going on here, okay? So in the ideal diode model, when that voltage Vx is positive, the diode is on and it looks like a short circuit, right? So what kind of amplifier that we've covered today would that look like? It's a unity gain buffer with a resistor between that input and ground, right? Because we have a wire providing feedback between Vx, the output of the op amp and the inverting input terminal. And the output is taken at that short circuit as well. So it's just straight up a unity gain buffer with a loading resistor, really, okay? So when Vn is positive, we expect this guy to behave something similar to a unity gain buffer, so the output should pretty closely follow the input. Now, when Vn is negative, since it's applied to the non-inverting input terminal, that means that Vx should also have a negative value, which means our diode becomes reverse biased. So what happens when a diode is reverse biased? It's an open circuit. So now we no longer have that feedback loop. So we no longer have a closed loop amplifier. We have an open loop amplifier. Can anybody remember what the open loop amplifiers we talked about in circuits 2 were? Special name for them. Comparators. Okay. And so what a comparator did, for those of you that don't remember, is it compared the input signal to some reference voltage. Whenever the input signal for a non-inverting comparator, which would be what this is, whenever the input signal was greater than that reference voltage, the output saturated to positive VCC, and whenever the input voltage was less than that reference voltage, the output saturated to negative VCC, or the negative power supply voltage, okay? So in this case, when we have an open circuit, when our diode is replaced with an open circuit, that resistor really isn't doing anything because no current can flow into the input terminals of the op amp because the input resistance is assumed to be extraordinarily large, on the order of mega ohms for a BJT based op amp and tera ohms for a MOSFET based op amp. So it's effectively comparing the input signal to ground as to whether or not this thing is going to go, when it's going to sync to VCC minus. Now, let's throw the constant voltage diode model in, which is a little bit more accurate than the ideal diode model, okay? So, with Vn set to 0, Vx, our voltage at the output of our op amp, should be approximately equal to VD on, such that V out is equal to 0 volts, right? So really Vn needs to be slightly higher than 0 volts for this to occur, but it can be a very, very small voltage will be enough to draw that Vx voltage up to VD on, because of the way that an op amp behaves, right? It's amplifying very, very small signals and giving out very, very large voltages because it's in an open loop configuration. With Vn greater than 0, Vx rises above VD on such that current flowing through R causes V out to still be equal to V in. So what we are getting here really is small signal rectification, okay? That's important because our basic diode-based rectifiers that we saw at the beginning of ELEN 335, we saw that the output looked similar to the input, but it was really scaled down by a factor because the diode didn't turn on until our input the output of the diode didn't occur until the input exceeded VD on. In this case, we don't have to have our input actually exceed VD on for our output to track and follow things here. So we're getting a 1-to-1 ratio of input to output voltages, even for very small input signals. That's why it's a precision rectifier. With Vn less than 0, the diode is off, and V out is equal to VCC minus. So our negative supply voltage, whatever that happens to be. So graphically, let's say that my input signal looks something like this. As a function of time, where this guy is Vn. My let's see. This is what Vx is going to look like. So it's just following whenever Vn goes above Vd on. It follows that. And then my output is just a rectified version. So the negative half cycles are chopped off of my input signal. So key here is that I effectively have a floating potential of VD on across or between the output node of the op amp and the output node of the system, and I can cause that to rise slightly, which causes current to flow through the system or flow through that resistor, which makes my output voltage exactly follow my input voltage. So this is how a precision rectifier works. It's a slightly more efficient way to rectify signals, especially small signals. Yes, sir.
This would be a more precise half-wave rectifier if I grounded VCC minus, or we have to ground it all?
So VCC minus, yeah, VCC minus doesn't need to be at ground per se, because when our signal, when it cuts off, right, it's just going to go to whatever it is. But the output is only going to see the positive half peaks. So all making VCC minus not 0 is doing, so here, down here is where VCC minus is, right? So it's just going to raise or lower that portion of the waveform at the output, but I'm still always going to have that VD on amount of voltage moving up and down as is necessary. All right, so that's enough out of me today. So we're finishing 4 minutes early. When we get back on, today's Monday, Wednesday, we're going to talk about logarithmic amplifiers and square root amplifiers. So logarithmic amplifiers occur when we put a BJT in the feedback position, and square root amplifiers occur when we put MOSFET transistors in the feedback position. So we can get some wild functions just by using simple op amp circuits. All right, thank you guys. The roll sheet did migrate my way. Okay.